Hey, Honors Biology, here's a screencast on chemistry of life. And basically we're just going to go on the basics of atom, matter, and elements, and important types of atoms we find in living things. And in order to understand how living things work, we have to first look at what it's composed of. Now, if you look at all living things, share that same chemical building blocks and depend on a chemical process for survival. So when we talk about matter, that's anything that occupies space, and we can break down matter into two categories: pure substances and mixtures. And pure substances is basically composed of, again, elements, the pure substance, for example, like oxygen, hydrogen, and iron. And when these elements react and combine, they form compounds like water, table salt, and ammonia. Now, mixtures, you will hear of homogeneous mixtures like solutions, like salt water, where it's evenly distributed, or they're heterogeneous mixtures like pizza, Italian salad, or like suspensions like blood. Now, elements are the simplest substance. As you can see on the periodic table, they're represented by symbols. They're the purest substance that cannot be separated into different substances by ordinary processes. They're the building blocks of matter, so atoms are the basic unit of matter, and so atoms make up the elements. There are 112 elements known today, and 92 are naturally occurring, and 96% of those elements that are found in living things are carbon, hydrogen, oxygen, and nitrogen. The major elements in the body, again, as you can see, oxygen, carbon, hydrogen, nitrogen, these form the majority percentages in the body. And then you have the trace elements that make up less than 0.01% of your body mass, and those are like these small amounts in the bottom, you see. Now, atoms is the basic unit of matter, and basically you have the nucleus in the center right here that has protons, which has a positive charge, and you have neutrons that has a neutral charge, and around the nucleus surrounds electrons, and electrons move in shells or orbits. And so the first orbit, or we also refer to as energy level, the closer the orbits are to the nucleus, the greater the energy. It only can hold 2 electrons, and then the next orbital can only hold up to 8 electrons. Now, if you look at the periodic table, the elements have an atomic symbol. So here, for example, Ca represents calcium, and then on top you might see an atomic number, and that number tells you the number of protons. And on the bottom you'll see an atomic mass. Now, atomic mass is determined by adding neutrons and protons. And you're wondering why not electrons? Electrons are added onto it, but the weight of electrons is so tiny and negligible that we don't even bother writing it in. So actually, and this number is actually an average of all the calcium isotopes that are found. And isotopes, later on we'll talk about, is atoms with different number of neutrons, but of course have the same number of protons. Again, the subatomic particles, electron has a negative charge, and we write electrons with the letter E with the negative sign. Protons, P with the positive sign, it has a positive charge, and neutrons are with small n, it has a neutral charge. And again, remember, electron has a -1 charge. So a neutral atom would have equal number of electrons and equal number of protons. Now, when the atom becomes charged, if you lose an electron, it becomes more a positive number, so a positive ion. Or if it gains electron, it becomes more of a negative number, it becomes a negative ion. The location of these particles is important. Electrons are basically orbiting around the nucleus like a cloud, and in the nucleus you just have protons and neutrons. Now, in life, the most common elements are carbon, hydrogen, oxygen, and nitrogen, and they are the major elements, they make up 96% of living organisms. And then you have phosphorus and sulfur. So if you know, like carbs, basically carbon, hydrogen, and oxygen. Lipids, carbon, hydrogen, and oxygen. And then you got proteins that can contain carbon, hydrogen, oxygen, and nitrogen, and sulfur. And then you have your nucleic acid that contains carbon, hydrogen, oxygen, nitrogen, and phosphorus. So all atoms of an element have the same number of protons, and protons is what makes up the characteristics of that atom. And so, for example, carbon has 6 protons, and this is a carbon atom, right? And if it has atomic mass of 12, that'll tell you that it has 6 neutrons. And if you remember how we figured that out, you take the atomic mass, subtract it by the atomic number, and that'll give you 6 neutrons. So atomic number, atomic mass, and your symbol. The number of electrons can be determined if an atom is neutral and the net charge is 0. That means the number of protons equal the number of electrons, which equals the number of atomic number. The atomic mass is the average mass of all the atomic masses of the isotope of that atom. Now, what's an isotope? Atoms with the same number of protons but different number of neutrons. So atoms of the same element will have the same atomic number, but the mass would be different. So here, for example, you have chlorine 35, atomic number of 17, and you have chlorine 37 with the atomic number of 17. So so it has, chlorine 37 has 2 more neutrons than chlorine 35. Now, radioisotopes play an important role in determining carbon dating. When we look at fossils, we look at the ratio of carbon, different, like carbon 14 versus carbon 12, and by looking at the ratio we can figure out how old something is. And each isotope has what we call half-life, and half-life is basically that amount of time half of the material breaks down. So when we look at the ratio, we can figure out how old it is. Now, compounds are formed when 2 or more different elements chemically combine. So here, for example, you have this metal, and this is sodium, and sodium by itself is very reactive, explosive, and chlorine, this green gas, is very toxic. However, when you combine it and they form a ionic bond, you have this inert substance called salt. Now, most elements combine with other elements making compounds. So compounds have a chemical formula, and it tells you how many atoms of each is in a particular compound. So for example, here you have water, you have 2 hydrogens and 1 oxygen. In carbon dioxide, you have 1 carbon and 2 oxygen. Sodium chloride, 1 sodium and 1 chloride, and so forth. Now, molecule, we sometimes we'll use molecule and compound interchangeably. A molecule is formed when 2 or more atoms join together chemically, and they can be the same atoms or different. So for example, you can have a molecule of water or oxygen, and they usually are covalent bonds. But all compounds are molecules, but not all molecules are compounds. So if you have a molecule of, say, hydrogen with 2 hydrogen atoms or oxygen atoms, these are molecules but not compound. Now, how do atoms form bonds? And all of that is determined by the electrons in its different orbits. Now, the circle shows where the electron will be traveling around the nucleus. So you have the first orbit where only 2 electrons can travel around that orbit. The next energy level or orbit, only 8 electrons can travel. And for sake of biology, usually it's just 8 electrons. Now, when you take chemistry, you'll learn that it can also go up to 18. Now, outermost electron is what's called valence shell. and this is where the outermost electrons are found. And these outermost electrons will determine what kind of bond that atom is going to form. So if it loses an electron or gains an electron, it will become an ion. So usually if it's less than 4 electrons, it's easier for that orbit to lose electrons. So it will form a negative atom. If it has more than 5 electrons, it's easy for it to gain electrons. Now usually if it's around 4, or sometimes they'll just want to share electrons. So the first shell can only contain 2. So here's an example of hydrogen. Hydrogen only has 1 electron, so it can share 1 more. So a energy level will want to be stable, and for the first orbit it wants to have 2, the second 8. So if it's missing some electrons, that atom wants to behave and search for those missing electrons to become stable. So here, for example, in oxygen, you have 6 electrons in the outermost shell and you need 2 more. So here 2 oxygen can share those 2 electrons. And water, for example, again, oxygen needs 2 more electrons, so it will share that 1 electron with hydrogen. And carbon has 4 outermost electrons, so it can share 4 more electrons. Now why 4? Because it needs 4 more to make 8 to be stable. So the types of bonds. Ionic, again, is where one loses and one gains an electron, and they stick together because of opposite charges. And a classic example is sodium chloride, our salts. Covalent bond is where they share electrons between 2 elements. And there's 2 types of sharing. One is unequal sharing, and that's called polar covalent. And one is equal sharing, and that's, for example, like a hydrogen bond. So remember, an ionic bond, sodium has a 1 electron in its outermost valence, and it can lose 1 electron. So when it loses an electron, it becomes positive. And chlorine has 7 outermost electrons, so it needs 1 more, and when it gains, it has a -1 charge. So these 2 will stick together because of the charge, and that's what we call an ionic bond. Now, covalent bond, remember, is sharing. So here you have 2 oxygen bonds that are equally sharing, and where in water you have these electrons being pulled towards the oxygen here, so we call this polar. And we call it polar because there's a slight charge here, so a slight negative charge in the oxygen end and a slight positive charge near the hydrogen. So that's why we call water a polar molecule, where this has an even pull and this is non-polar.